Hello, good morning everyone. So we are continuing with the chapter Boolean algebra, and in the previous videos we discussed about logic gates. So today we are going to discuss about universal logic gates and some examples based on that. So what is universal logic gates? Now when you talk about the fundamental logic gates, you saw that you have AND gate, OR gate, NOT gate, and then you in the videos also you saw about this NOR gate, right? NAND gate, then XNOR gate, and so on, right? So now we have already come across this NAND gate and NOR gate in the previous videos, but now why are they called as universal gates? So NAND and NOR gates, they are called as universal gates because they can create all digital circuits without using the other gates. So without using AND gate or OR gate, NOT gate, okay, uh, all of the other gates, using only these two gates you can create the digital circuits with these two gates only. Why is because all the other gates can be created using just these two gates, and using these two NAND gate and NOR gate you can create the other fundamental gates also and the derived gates also, right? Now based on that, let's see how it is implemented. So implementation of NOT and OR using NAND gate. So that means that how you can create the NOT gate, AND gate, and OR gate using this NAND gate. So first we are going to see that how the NOT gate is created using the NAND gate. Now you remember that in case of NOT gate, it accepts only one input, and then the output is the complement of that input value. So that is x, output is x complement. So if input is 0, output will be 1. If input is 1, output will be 0. So you know that using the NAND gate, originally in the case of NAND gate, it accepts 2 or more inputs, but in the case of NOT, it accepts only one input, and whatever be the input number of inputs, be it 1 or 2 or 3 or 4, the output for all the gates should be only 1, right? So in the case of here you can see that this is NAND. So NAND means it is, in this particular symbol is AND gate, but NAND means, okay, here you can see that this circle, this represents the NOT gate, right? So in the case of NOT gate you can see that the two signal points are joined together to so that only one input will be accepted from for the NAND gate. So this is the symbol, okay? So because of this, instead of two inputs, only one input will be accepted, and then from there you will get the complement, right? So that way you get 1 0 or 0 1, right? Now AND gate using NAND gate. So you can see that you're using two NAND gates here, but in the first case you can see that you can accept two input values from x and y variable, so x and y literal, and then the result is that the output will be x and y the whole complement. Alright, so that is x. So because of this NOT, right, so the output will be x and y, but because of this NOT operator means what? It is the complement, right? So it will become the whole of this complement, because here you have two variables, but the output will be only one value, right? So you join these two because of this NAND gate, because NAND gate represents the multiplication dot, right? So it will, the outcome of this will be x dot y, x and y, it will be 1 1, it will be 1 into 1 1, right? Or 0 0, it will be 0, or 0 into 1, it will be like that. But in here this is in this case, suppose like this is positive numbers, right, high, so here it will be x dot y, but because of this NOT operator, it will become the whole complement. Now from here there is only one output, so now we have to give into the signal as only one input value, so that's why this is joined together, and then the outcome of this will be, as you can see here, you get the AND gate. So in this case it will be like x dot y the whole complement. Again, once you reach here, it will be again the whole complement. So complement, and as you can you know that you have the different Boolean laws, right? So based on that, you saw that x complement, the whole complement, gives raised to x, so that erases the complement. So in this case it will be x dot y. So that's why you get AND gate. Now in the case of OR gate using NAND gate, you can see that here, as you can see here, you are using 3 NAND gates. Here you are using only 2 NAND gates, but here you are using 3 NAND gates. So you can see here that x only one input, y only one input. In here 2 inputs, but in here one input is represented by one NAND gate and another input is represented by another NAND gate. So the outcome of that will be the x complement and y complement, because only one variable value, right? So since because of this NOT gate, so you get the complement of that. So now you have two input values, that is x complement, y complement. So when that is sent as two input values to the NAND gate, the outcome of that will be x complement dot y complement, the whole complement, because now you are finding out the complement, right? So now what happened is that based on the Boolean laws, right, that is the De Morgan's theorem, okay, the De Morgan's theorem. So you get this output, that is, you have two theorems in De Morgan's, right? So x dot y, the whole complement, is equal to x plus y, right, the whole complement. So here you can see that x complement plus y complement, which is complement of complement is x, and complement of complement becomes y. So you get the output x plus y, which is the OR gate, right? Then implementation of NOT, and OR using NOR gate. So now we will see that the NOT gate, and 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 OR gate can be found using the NOR gate also. So you can see in this diagram, so this represents the NOR gate, right? So in the case of NOT gate, since only one input, so you can see the symbol here, one input and then one output, the complement of that. So 1 0 0 1, right? So in the case of NOT gate, it's very simple. You just have to change this symbol from the NAND gate to this NOR gate format. Now in the case of OR gate using NOR gate, you are using two NOR gates. You can see that two input values are entered, x and y. Because it is OR gate, that means you have to do you have to use the plus symbol, right? So here x y, then what you get is x y. In the case of NOR gate, it will be x plus y, but because here, because of this NOT gate, you get the complement of that. So that's why x plus y, the whole complement. And since only one output is generated, so only one input has to be passed, so that's why this is joined together. And in here what you do is that, since because of this you get another complement, so that is x plus y complement, the whole complement. So according to the Boolean laws, so what you get is x plus y. So that's how you get OR gate using the NOR gate, right? Then you can also get the AND gate using NOR gate. You have to use 3 NOR gates. So here x is one single input, y is another single input for these 2 NOR gates. The outcome of that output is x complement, y complement. So since you have 2 input values from 2 NOR gates, that will be passed to this NOR gate as input value. The outcome of that will be x complement plus y complement, the whole complement. Alright, this is normal. Till this part is normal, x complement plus y complement. But because of this symbol, the NOT gate, it will, that means the complement of that, right? So that's why you have here x complement plus y complement, the whole complement. Alright, then just like this, you can see here x, and when it gets output you get x complement, right? But in the case of this, how you get this is because already this is x complement, already this is y complement. So what you do, using NOR gate, you add it up, right? Here it is single, but here the output has to come out in a single way. So that is why x complement plus y complement, but this is a complement, so you get the whole complement. So what you get is De Morgan's law. You get x dot y based on that, right? So using that, what we do is that in your solve exercise also there are lots of that you can perform this. Draw the following circuits using NAND gate, right? So using this, so you have this x dot y plus x uh, complement y complement x. So here based on that you draw this diagram like that, okay? And then you have to write the solution in this format, right? So that is x y, so x dot y, all right? So x dot y, and then in here y complement x, okay? And since you know that how many, be it how many inputs you get, the output will be only one. So that's why you have these three NAND gates, right? So it's up to you to find out, okay, what will be the output of this, okay? So try it out and then check out what output you get based on that. So keep in mind that this is a complement, right? Okay, so that will be a complement on that. And then now draw the following circuit using NOR gate. So here also NOR gate is x complement plus y plus z dot x plus y, x plus y complement plus z. So here based on that you can see the three literals are assigned to the NOR gate. As I said, it can be two or more than two, also three, all right? So in the same way here, x y complement z, right? So what you get is x plus y plus z, and here x y complement z, all right? So here also, since you desire one output, that's why another NOR gate is added on that. So what you do is that you try out the how to find out the output on this one, okay? And then from here the input will be entered. Again the final output will be uh, a different way, all right? So likewise, there are lots of this kind of uh, examples in the solve exercises, so go through that, practice as much as possible on that, all right? So if you have any doubts on this, you can ask, okay?